Dan is also, I'm very pleased to say, the president of the General Society of Mechanics and Tradesmen. Now, as you may know, Dan has officially retired, so it's very generous of him to come back and share his expertise with us one more time. Dan Holohan began his love affairs with heating systems in 1970 by going to work for a New York-based manufacturer's representative that was deeply involved in the steam and hot water heating business. He studied hard, prowled many basements and attics with seasoned old-timers, and paid close attention to what they had to say. He founded heatinghelp.com in 1997. His daughter, Erin Holohan Haskell, now owns and operates this extensive resource. He's also the author of literally dozens of books and literally hundreds and hundreds of magazine articles. He is very proficient, all devoted to heating systems. He was an established speaker in high demand on the seminar circuit, having taught more than 200,000 people prior to his retirement. It is my huge pleasure to introduce to you Dan Holohan.
Thank you so much for coming out.
So, systems. When I first looked at this thing in real life, I was scratching my head. I said, what the heck do we have here? This is what's called a vapor system, and it was very, very common. It ran into these out there in the field, and everything in this drawing has to be just like they show in real life. I mean, in real life, it's got to be just like they show in the drawing. The dimensions have to be just so. Everything's got to be just exactly like you see here. And when you first go out, if you don't know, if you haven't read, you'll say, okay, there's two check valves here. What do the check valves do? What the heck is this thing? Because some of these that you see on jobs are like 4 feet high and 4 feet wide, and they're hanging up there near the ceiling, and you look at it, and it looks at you, and it goes, let's get it on, right? And you know what you do if you don't know what that thing is you put your hands in your pocket and you back out of the boiler room. If you don't know what it is, it's probably really important. So you see up here it says that this is an air eliminator with a check valve. Now you see this little thing here? It's a 3/4 inch tapping. That's the air vent for the whole system. It looks like that. It's hiding up there. You can't see it. It's the only air vent in this system. This steam trap over here is not trapping steam. That's an air vent. It's passing air from the end of the steam main into the steam return line so that it can vent out of that little gizmo up on the top there. If that trap goes bad, you'll never know it, and that trap will then put steam into the return line, and the entire building will stop heating. So when you go out to troubleshoot, the first thing you do is you grab hold of that pipe to see if it's hot. If the pipe is hot, you know that trap has to be repaired. And once you repair the trap, everything starts to work again. But this little guy, if you don't have the book to know what that little guy is, that's an air vent, and that little ball in there gets pushed up by the air when it's leaving, and then falls back down, and then the steam condenses, because when you turn water into steam, it expands 1,700 times. It goes off like popcorn, and it pushes all the air out of the system, hits the cold metal, and turns back into water. And if you can set it up so that the air can't get back into the system, and that's what that little ball does, such a simple thing. The ball falls down, the air can't get back in. The whole system goes into a deep vacuum. And in a deep vacuum, in the days when they were burning coal, you could boil water at temperatures as low as 160 degrees, and that's why they called it vapor heating. Because this steam would just waft off at an amazing velocity. Steam in a vacuum travels way faster than steam at 100 psi. The lower you have the pressure, the faster the steam will go. So walk in there and you find out somebody might have taken that thing out because they raised the pressure too high and it was blowing steam out of there, or traps in the building may have gone bad and the steam is blowing into the returns and blowing out of that little hole. So some knucklehead will go in and take that thing out and replace it with a pipe plug, because pipe plugs are cheaper than air vents. And at that point, the laws of economics override the laws of physics, and now you have a building that won't heat because somebody went in there and took the air vent out and put in a plug. See? What things do, you can find the purpose in the name. So, air vents, steam traps, condensate pumps, plugs, plug. In plumbing, P-traps. There you go. So, knowing that, you start out where the steam is being made and you walk through the system and you look for an air vent, because there's never been a steam system made that didn't need to be vented. These things breathe like we do. On every cycle, they have to be expel all the air, and then they fill up again with air when they shut down, and it's breathing in and out. That's why you get rust inside these systems, because everything's wet and you bring in air back in on it all the time. So the pipes begin to rust, the radiators begin to rust. All that stuff washes down into the boiler. So I would go in the boiler room and say, if I were air, how could I get out? And then I'd start wandering through the building. You walk down the ends of the pipes and you look for an air vent. This is the best part of being a heating guy, because you can go anywhere. You go into some of these mansions, I'm just nosy. I want to see how these people live. I'm going to go upstairs, I'm going to poke through the rooms, I'm going to look in the desk drawers. I'm the heating guy. What are you doing? I'm trying to get the heating working, right? So I'm looking for the air vent. Could be here. What's over here? What's under the bed? Could be an air vent. Wander down the end of the line and you see, okay, there's the green air vents, and what's on the pipe there? That's what we call pipe vomit. This is what happens when the pipes can't take anymore and it just spits all that crap, all that rust, out of its top, down onto the pipe, and as it's spitting all that rust, the rust gets into the little hole that's in the air vent that's supposed to vent the air and plugs it up. At this point, some knucklehead shows up and raises the steam pressure, thinking that that's going to get more heat out to the building. When you raise the steam pressure, not only does the steam go slower, but also it compresses the air that can't get out, which causes you to raise the pressure even higher. See, it feeds on itself. So, knowing that the air vent is plugged up here tells me why there's no heat in the rest of the building. So with steam, I learned at an early age that the problem and the cause of the problem are rarely in the same place. You got to get out and be nosy. You got to wander around. So if there's banging over on this side of the building, look over on the other side of the building for what's causing it. When the banging happens also tells you what's causing it. Does it happen at the beginning of the cycle, in the middle of the cycle, at the end of the cycle? All these things give you clues into when it's happening and what's going on. So when you see an air vent installed like that at the end of a main, what's happening inside of it is that the water and the steam moving at 60 miles an hour, that's the design velocity for steam system, hits that elbow and just bounces up because water's not compressible. And it just takes all the crap that it's bringing along with it and its own force and just smashes it into the air vent and destroys the air vent. And that could happen on the first cycle. I've had people say to me, that vent can't be failed, it's new. I said, well, I bought eggs. I was carrying them home from the store and I dropped them. They broke. They shouldn't have happened because they're new. How could they break? So vents on mains are supposed to be installed like that, back off the end and up high out of the way of all that crashing that's going on in that last elbow there. So you move the stuff back and you say, okay, that keeps the vent from squirting. Because if the water is being driven by steam and there's an air vent and the water can't get out of the way, it's going to come squirting out of an air vent. Sometimes it's squirting out in the apartments where the people live. My daughter Meg was a wonderful, wonderful child. Well, she's a woman now, and she'll always be my child, but Meg lived in New York for a while, Her sister bought the heatinghelp.com business. She's into heating. Meg works for the international development, our foreign aid program. She works with tuberculosis. But she was living in an apartment house in Manhattan, and she called me up one day and she said, "Dad, there's this pole in the kitchen, and it's got this little silver thingy that's squirting water." I said, "Who is this?" She said, "It's your daughter, Meg, your favorite." I said, "Who is this? How did I raise you?" So she was never bit by the bug, but I love her anyway. But sometimes the vents squirt, and then the knuckleheads show up, and they're going to solve these problems. So this was one that happened out on Long Island. So the people added an extension to the back of the house. Out over the back door, they put a separate room, and it's an old steam heated house. So they ran a steam main off the main that was feeding the rest of the house horizontally into the crawl space, like dead level, because this was a guy that felt that pipes really had to be level rather than pitched. He wasn't thinking like water wants to flow downhill, right? So dead level pipe going out and then up into this radiator that was on the far side. And naturally, the steam goes into this cold crawl space and it condenses. There's no insulation on anything, so it condenses, and the water can't drain back against steam that's coming at it with a gale force wind, so the water starts squirting out of the air vent that's on the radiator. So the plumber comes back and he solves it by putting that soda bottle over the air vent. Just cut a hole in the side, put it over the air vent, and then he took the garden hose and stuck it on the bottle and drilled a hole so it would go down into the crawl space. So let's go into the crawl space. Okay, so here we are. The hose into the basement, and then we go down the basement, and it's the back of the stoop here, and it just goes into a slop sink. And should it get clogged up again, we're all set with the Drano. So and it always makes me ask the question: who gets to work in America? Everybody. Right? And since we don't have any inspectors on heating, we do on plumbing, we do on electrical, but with heating, anything's possible, right? And everybody gets to work on it. So there you go. So you can't make this stuff up. We also remove insulation and we don't replace it. We take it all off and we don't replace it because suddenly the basement's warm and cozy. Isn't that nice? It's so nice. But you got to keep in mind that when the system was originally designed, it was designed to run on low pressure with all the pipes being insulated because steam wants to turn back into a liquid desperately. It's not natural for it to be in that state. It wants to be liquid like the ocean. So it tries to give up this heat to anything that's cold. And if you remove the insulation from the pipe, you increase the heat load of that pipe by 5 times. So we go into a building, we look, and what do we find? We find asbestos, which, you know what it is. As soon as you look at it, you see it up on the pipes, and you say, oh my gosh, this is going to be horrible. It's going to be expensive. We've got to get this stuff abated. But know that it wasn't always horrible. It used to be the magic mineral. It was the magic mineral, and it was touted for pipe coverings on steam and this Chalmers Spence company. I looked to see what was there at 419 8th Street. There's a bar there now, so I thought that was appropriate. So, and there was time when it was fun. Like, don't take a break for the summer. Summer is the perfect time to round out your asbestos collection. Hey, who knew, right? It was great stuff while it lasted, and now suddenly it's not so safe anymore. But there's a lot of things that are not so safe anymore. I mean, I love this from Ronald Reagan sending all his buddies Christmas presents of Chesterfield cigarettes. I wonder how they're doing. So, there's things that we know are dangerous now that we didn't know then. And when we take the asbestos off, a lot of times it does not get replaced with fiberglass insulation because we don't want to spend the money. So we had a building that was heating okay, but now we remove all the pipe insulation, and suddenly the stuff that's nearer the boiler is getting hot, and the basement's nice and warm, the garage is warm, because we got all the asbestos off, but upstairs is cold. So some knucklehead comes along and raises the pressure, thinking that somehow if you raise the pressure, you're going to increase the output of the boiler. Think about this. If you've got a million BTU boiler in a building with 1 million BTUs worth of radiation, That includes insulated pipes. And you remove the insulation, suddenly the load on the pipes goes up by 5 times. Suddenly you've got a 1,000,000 BTU boiler with maybe, 1.25 million BTU worth of stuff that can condense steam. And the steam doesn't care. The steam just goes out and it turns into water on anything that's cold. And you wonder why it's not getting hot at the end. You see? All you got to do is put the asbestos back on and things go back to the way they were supposed to be. So, a lot of things we learn as we go along. Okay. I'm moving that by magic. Oh, we don't clean the system, too. That's another big thing that we don't do is, we figured put it in, it's good enough, we don't clean it. But I could show you some of the old heating books I had that were written in 1910 and earlier, in 1920 and later, where they said no system is completely finished unless it's thoroughly cleaned. And this is when the thing was brand new. If you're replacing a boiler, you're not replacing the pipes and the radiators. So you're taking a pristine boiler and you're putting into a system where it's going to act like a scouring pad on all those pipes that are up there with the rust inside of them, and all of that stuff is going to come flooding back by gravity right into your brand new boiler. So we're supposed to be cleaning these systems, and that's why the boiler manufacturers will give you things like skim tappings, which you see here. So it's a big hole in the side of the boiler at the water level, because that's where the oil is. Oil lays on water, and the oil comes from the manufacturing process. In the foundry, when they're making the boiler, they have to machine it so you can screw pipes into it, and that involves tools that use oil. That's to keep the tools from going on fire when it's rubbing against with the friction. So all of that oil gets left in the boiler, and it comes out as soon as you start running the boiler, and it lays inside the boiler, and it's very difficult for water to steam through oil. So you wind up with this kind of a rubber sheet laying on the top that is the oil, and it causes very violent boiling inside, and you start to get, it's what's called priming, and that's where water's shooting up into the system and out into the pipes. The boiler goes off on low water. A low water cutoff comes on to replenish the water, to keep the boiler running, and then all the stuff comes rushing back from the system, and now the boiler's flooded. So somebody's got to go and drain it, and that involves sometimes chemicals that are being thrown away. It involves hot water that's being thrown away, and it just keeps increasing the fuel bill. So the system needs to be clean. And the skimming gets rid of the oil, particularly on startup. So once the boiler goes in, you give it a week or so to run, and then you go back there, and you just shut the boiler off, and you turn on the cold water, and you let it drift to the center of that T. So you're right at the water line where the oil is, and you drain out of a pipe into a bucket, and you just pump it somewhere, and you spend time doing this. And it could take you sometimes days to get this right. I've had people call me up and said, I skimmed the thing like a dozen times, and it's still doing this, still violent. I said, do it again. And they'll do it again like the 13th was the time. And they get it. And the way you check it, if you're a pro doing this stuff, is you get yourself a 2-inch pipe, and you put a cap on the bottom of it, and you make sure it's clean, get all the oil out of that pipe, and then you take a sample of the water as you're blowing it down, and you heat it with a torch. Don't hold the pipe in your hand while you're doing this. You learn about conduction. So you heat it with the torch, and then you look inside to see what it's doing, whether it's boiling violently or not. If it's boiling violently, or you can actually see the oil in the water, it makes like a rainbow shade in there. Go back and skim some more and skim some more. So I tell people that, if you're quoting on a boiler, if you're a contractor, or if you're a building owner, expect the smart contractor to say to you, this needs to be cleaned. This may be why our price is higher than the other guy's price, because we're going to clean the system for you. And if you say, well, I don't think that is necessary, I'll go with the other guy. That's fine too, because sometimes those people need to get together. The guy that's looking for the cheapest price and the guy that wants to do the lousy job. They should find each other all the time, because then they'll call the good guy and pay him. So how do you figure it's, because cheap is expensive. You got to pay a lot of people to do it again and again and again until you get it right. So nowadays with the boilers, if you're cleaning, there's chemicals for this and all that, but a real good product to use that's been used for many years is called Mex, and you can pick this up in any hardware store. And Mex is just a really, really strong cleaner. And it's soap. So it's not going to hurt anything in a boiler. It won't hurt rubber gaskets or anything like that. It's not like adding petroleum products to something that has rubber in it. And the Mex is, you just use 1 pound per 50 gallons of water in the boiler. You don't need much of it. You put it in there, and heat it up in a bucket, throw it into the boiler, and just let it steam. I'll show you how to get rid of it later by using valves on the boiler. But that's what we do. And while you're at it, check the pH scale on the boiler water. Because, perfect is 7. Anything lower is acid. Anything above that is alkaline. Alkaline's as scary as acid. When we talk about Drano, because it's safe for pipes, what's the pH of Drano?
3.
Just the opposite. Drano is an alkaline. Drano is like way, way up there on the scale, probably 13. That's why it won't hurt pipes, but it'll hurt everything else that's in the pipe. It'll just dissolve it. But when you boil water, you're breaking down carbonates and bicarbonates that are natural to the feed water, which is basically dead stuff. So this is the stuff that comes in from outside. And when you break down carbonates and bicarbonates, what you get is carbon dioxide. The carbon dioxide goes off with the steam, mixes with the water, and forms carbonic acid. And that's what eats pipes. And that's what causes steam boilers to tend to go down toward the acid side as they're running. That's why pipes begin to fail, particularly return pipes, because there's no great fast flow through there. The water just sits in them. And if that water is acidic, it's just going to go to work on the metal. So classically, we've raised the pH of boiler water by using baking soda, which is an alkaline. And if it goes too far on the alkaline side, we use vinegar to push it back the other way. And they balance it back and forth like that. That's classic old-timer stuff, vinegar and baking soda. The one thing I caution you about, though, is with the vinegar, if you put that into a system that has air vents in the radiators in the rooms where the people are, they're going to smell the vinegar. And people will complain about that. Some people will be afraid that it's carcinogenic even, but it's not. But use lemon juice. It gives you that lemony, fresh smell, and people will be a lot happier. One time I was looking at this apartment building where they had very, very fancy buildings, and the people called me up to look because there was this tremendous smell coming out of the radiators, and I went there to look, and I smelled, and it was clearly urine. I mean, you could smell urine, I mean, we had 4 little daughters. I know what urine smells like. Right? So I said, let me go downstairs. And I went downstairs. I met the superintendent. And I said, man, you must do so well here. You live here? And yeah, he said, lives in the basement. I said, man, these rich people must give you great tips at the holidays. And he says, yeah, you would think so. He says, but the poor people give you the tips. These rich people don't give you anything. I said, well, what can you do? He says, what can you do? He says, I'll show you what you could do. This guy had this big, like Costco-sized coffee can that he was saving his urine all day long. And then at night, he had a funnel. He'd take the relief valve off the boiler, and he poured this stuff into the boiler and sent it upstairs. He says, that's what you could do. So, never overlook the people that are in the building. So, if the pH is going acidic, it's going to cause the pipes to corrode. If it's going the other way, alkaline, it's not going to cause the pipes to corrode. In fact, when you get up to a pH of 9, or close to 10, corrosion is impossible at that point. But what happens when you go a tad higher than that is the water will begin to foam. High alkaline water makes the water foam on the surface. So you get these bubbles that are very tough. They don't want to break. And it's very, very difficult for the steam to bust through those bubbles because the liquid water in the bubbles is condensing the steam, and also that carries off into the building. So you get this priming, surging, all these bad problems that happen if the pH is too high, and that's why they use the vinegar to move it this way and the baking soda to move it that way. So when you're blowing down a boiler, get yourself some litmus paper or a pH meter, because it's fancy now. We've got electronic things that do this, and just check the pH. Ideally, it should be somewhere between 7 and 9 for steam heating. Okay, this is a big one in my mind. We line size steam traps. So we look at a trap and we say, what size is that? Is that 2-inch? Give me a 2-inch trap, because we got a 2-inch line. In the basement here, when I first got here, there was one trap for the whole building before the condensate got dumped. Because when you have Con Ed steam, you don't return the condensate to Con Ed. You have to lower its temperature and then dump it into the sewer. So there was a trap in the basement. John, what size was that? Is John still here? Okay, he's like, I think it was like a 2.5-inch trap at the end of this system. And I looked at that, and the reason why it was a 2.5-inch trap is it was a 2.5-inch pipe. There's now a 3/4-inch pipe doing the same. A 3/4-inch trap doing the same thing, and it's oversized. So traps don't need to be or should not be line-sized, and when we size them that way, we're going to be wrong every time. I'm not talking about the radiator traps. Here you've got a trap that's connected to the radiator over here. It's got a bellows that's filled with a mixture of alcohol and water that's set to boil at about 180 degrees. And at the factory, they put that stuff in the bellows and they heat it so the stuff starts to boil, and then they seal it while it's boiling, and then quickly remove the heat. So the stuff on the inside condenses, and that bellows just shrinks up on itself. So the next time the steam comes up, it heats the stuff that's on the inside of the bellows, and that causes the bellows to distend, pushing the pin down into the seat, and the trap is closed. At this point, you need to have about a 10 to 15 degree drop in temperature before that trap will reopen. So you can check this sort of a trap with a thermometer. You take a temperature across it. Those electronic things that have like a little laser pointer are cool. You check this side, check that side. You should see about a 10 degree drop in temperature from one side to the other. And those are typically line size to whatever size goes into the radiator and out of it. But a floating thermostatic trap is quite different, because the thermostat here is there strictly to pass air. So the air comes into the trap ahead of the steam, goes there somewhere downstream. It's going to be vented from the system. And this is a normally closed trap. It's the weight of the float magnified by the length of the lever, and it pushes the pin into here. So when the steam comes in, it can't get out until it turns back into water. When it does, it causes the float to float up, and that pulls the pin out of the seat. But if you think about two-pipe steam, there's a steam trap on every radiator. And the only thing that floating thermostatic traps are handling is the condensate that forms in the main feeding those radiators. So you might have a trap on a line that's 300 feet long. Let's say there's a 2-inch line that goes up 300 feet in the air. The only thing that trap has to handle is the amount of condensate you're going to get by heating 300 feet of 2-inch pipe. It's not much condensate. So that would be a 3/4-inch trap. But I guarantee you at the bottom of that trap, you're going to find a 2-inch trap, because that's the size of the pipe. And when you've got an oversized trap, first of all, you paid a lot of money for it. And secondly, when the condensate forms, it barely moves that pin off the seat, because there's not that much condensate. And as it does that, the force of the steam starts to shove the water through that door that's almost closed, and it causes erosion. It's called wire drawing, and the metal fails. So an oversized trap is going to fail real fast. And then you're going to buy another one, and guess which one you're going to buy? The same one, because that's the size of the pipe. So if you don't know how to size steam traps, get together with a steam trap rep, or go on a website like heatinghelp.com and read and find out how to do it. It's not complicated. If I'm able to do it, anybody could do it. And you size it properly. But I can tell you this with 100% certainty. If you're dealing with heating and you see a float thermostatic trap that's the same size as the pipe, it is the wrong trap in every single case. You paid more than you should have, and the thing's going to fail. And when the floating thermostatic traps start to fail, now's when you get the steam into the returns, which shuts down the heat for the whole building. So they're critical, and if they're line size, they're wrong. It's a good place to look, because that's a mistake that's always made. We undersize or oversize the replacement boiler. Now, I say that because this is like an evaporator and a condenser. The boiler's the evaporator, the system's the condenser, and these two things have to match. So the only proper way to size a replacement steam boiler is to go everywhere and measure all the radiators. The boiler's ability to produce steam has to match the system's ability to condense steam. If you could do that, you're good. So you walk in there and you look, you might have these, what are called tube radiators on the right, or on the left, or the column radiators on the right. This is a true steam radiator because they're not connected. The sections are not connected across the upper portion, just along the bottom. So the one on the right is used for one pipe steam, and the one on the left is used for two pipe steam. So if we had a radiator like that, a 3-column radiator, the columns are what you see on the side, 1, 2, 3 over here. You count the sections. So let's say that's 9 sections, which it is, and the radiator height is 38 inches. In this case, we measured from the floor up to the top. That means that each section puts out 5 square foot of radiation. 5 times 9 is 45. That's 45 square foot of equivalent direct radiation for that radiator, and that would be equal to 10,800 BTUs. 1 square foot of radiation is 240 BTUs. You go to the next radiator, measure that. Next radiator, measure that. Right? Go from place to place. This is where you get to be the heating guy. You get to go everywhere. Very simple. We don't think like air. You know, we should be thinking like air. If I were air, could I get out? You start in the boiler room or wherever the heat's coming from, wherever the steam starts, and you walk. If I were air, could I get out? And you also think about the air in the space that you're in, because in some systems, you're going to run into this thing called indirect heating. And this is a system that has these, what are essentially boiler sections, but really radiators. They're concealed inside ductwork, and they take in 100% outside air. You find these in a lot of the mansions. A lot of buildings on Fifth Avenue had those old homes. And the air comes in from the outside, and it goes up into just wafts across the hot metal and goes up into the space. There are no return air ducts. The return air ducts are the drafty windows. So you heat the air from the outside, and it just migrates out through the windows. When they modernize these houses, they change the windows. So suddenly you've got no way for the air to get out of the space, so the air stops coming into the space and the heat stops coming up. So I fixed the window to save energy, and now I have no heat. So this is where you have to give the air a way back into the basement, and sometimes that involves just changing the basement door to a louvered door so that the air can get back down. So you think about, like, if I were air, how could I get out? And you start to see yourself as air. You start to think about convective currents and the way the air is going to move up into the building and how high is it going to go. You question things like that. How high will the air go? If you were in a cathedral like this, or even a space like we're in right here, and you went into a cathedral like that and did a heat loss on the building because you're going to replace the boiler, you will find that the number you come up with is so dramatically greater than the actual boiler size and radiation size that has been in that building for 100 years. So how can you possibly heat that building with something so small? And everything in your being, if you're a heating professional, is telling you to put in something bigger because you don't want to make a mistake. So it might be 4 or 5 times bigger, because look at all this space I have to heat. But if you think about it, like what I call the dead men thought about it, those people that put this stuff in, you're not really heating the whole space, because nobody's walking in that area above 6 foot, right? So there's really no reason to be heating all up there. So what they did back then, when they were heating buildings like this, cathedrals and government buildings and high spaces like this, is they would put in radiation that would send up, well, first of all, heat people, because radiators radiate about 40% of their energy and 60% is by convection. But they would set it up undersized so that the convective currents would rise up
and stop. So it becomes like the atmosphere. You have the troposphere, the stratosphere, the ionosphere. Troposphere is where all the weather's going on. You got all these convective things going on down here. Stratosphere, that's the jet stream up there, right? It's going sideways. And the ionosphere, pretty much nothing's happening up there, right? So what they do inside of a big building like this is they set up these convective currents that are relatively low so you can heat the people without heating all that space. And they learned about this in the 70s after the 73 OPEC oil embargo, when they went into buildings like churches, particularly, that were trying to save on energy because the fuel is now so expensive. And somebody said, well, you know, heat rises, which it actually doesn't. Hot air rises. Heat radiates. But hot air will only rise to a certain point and stop rising once it loses its heat energy. But they think it's all the way up there by the ceiling. So they said, oh, there must be a lot of hot air up there by the ceiling. So they put in ceiling fans to take all that hot air that wasn't there and pump it down to where the people were. So they put the ceiling fans in the churches, and it takes this cold air that's up there, like it is in the stratosphere, and they bring it down into the bottom of the troposphere, and it lowers the overall air temperature in the whole church, which causes the thermostat to click, which makes the fuel bills go even higher because of the damn fans up there. Which is why you'll never see those fans running in a church in the winter. You'll see them in the summer because they're trying to cool people off. But even in this magnificent space that we're in right here, this whole area here has got two radiators. One of them's behind this bookcase, and the other one's over there behind that bookcase. So how do we do this? But if you look up at the glass, see those pipes running around? Those are steam pipes. That's to keep that glass from sweating. Because the people that did this job said they knew that the heat from that radiator is not going to go up into that skylight. It's going to cool down on the way up. So you got to put additional convective currents going on up there to keep that glass warm so it doesn't condense on the inside and rain down on everybody in the library. This stuff's right in front of your eyes, right? So when we're sizing, we have to think like air. We've got to think about like what's air going to do when it comes and goes like that. We also install one-pipe steam on two-pipe steam radiators, and to me, this is the jerkiest thing you could do in the whole business. To put a one-pipe steam air vent on a two-pipe steam radiator. It is magnificently stupid because, you know, there's a rule in steam heating that says, when you do something stupid, you will always be rewarded in a small way that leads you to do things of greater stupidity. So by putting a one-pipe steam air vent on a two-pipe steam radiator, you're rewarded because suddenly the radiator will get hot because you let the air out. See, this is the way it's supposed to work. The steam comes down the line, and it starts to climb the ladder. Those are the radiators. Those red things on the outside are the steam traps, the radiator steam traps. This blue thing at the end of the line is the floating thermostatic trap. So it's pushing the air ahead of itself through the trap into the return and venting somewhere in the boiler room. That's the way it's supposed to work. But now let's say one of those traps goes bad. Let's say it's the trap on the first floor. Goes bad, it fails in the open position. It's not going to call you to say, listen, I'm not working anymore. Because that trap in a typical New York City apartment building is cycling 350,000 times a heating season. So manufacturers of traps give them 10 years tops. They get replaced every 50 years, if they're lucky. Right? So traps fail, they're open, and they're passing steam into the return. So you get this, it goes down the end of the line, and suddenly it passes through the radiator and into the return. Now you see here we got steam in both the supply and the return, and none of these radiators will get hot because the air is trapped in them. So this is where some knucklehead goes in and puts one-pipe steam air vents on those radiators up there. Now the radiators get hot. And he says, I'm the man, right? Look at me. But how's the water going to get out of the radiator? There's steam in the return looking for the air vent. Steam's coming up both pipes trying to get out the air vent, and the water is not able to drain down. So the radiators fill up with water. The boiler goes off on low water. The low water feeder comes on to feed more water into the boiler, which is now going to flood, and the water starts to squirt out of the air vents upstairs. If you got steam traps, they must be maintained. There's no way around that. Can't fix that with air vents. And we also assume the piping is correct because it's been there. So when we look at the way a modern boiler has to be piped, there's certain rules with it. First of all, you've got to use multiple tappings because the modern boilers produce steam at much greater speed than the old ones, because the old ones were big boilers. These are relatively small, and you got the same output coming out of them. So we look at this pipe here. This is the risers that go up to the boiler header, which is taking all the steam out of the boiler. That's got to be at least 2 feet above the top of the boiler. And it turns and it goes over here toward this T, and we want to make sure that that T is on the left side of those risers so that the steam and the water that's coming out of the boiler is traveling in the same direction. Up here we've got a valve that a good steam contractor will tell you you need a king valve. It's not a special valve, it's just a gate valve or a ball valve, a big butterfly valve, say a ball valve, that goes up there on the supply side, and another valve on the return, so that once a year we can close those two valves and isolate the boiler from the system, turn the burner on, bring up about 10 pounds of pressure, and then open that valve that's on the bottom of the boiler. It's going to take all the crap that built up in the boiler and what's called the mud leg of the boiler, appropriately named, because it fills up with mud, which is the metal that's coming down from the system, and it blows it out of the boiler. Those two valves, you'll spend a little bit more money on to go in, but they will save that boiler. And it'll last for years and years. And while you're at it, on the return side, you put this drain valve there on the bottom too, so you can waste the condensate as it's coming back after you put the mix in. Shut the valve that goes back into the boiler and open the drain valve and just let that crap waste out of the boiler, so it does waste out of the system so it doesn't go back into the new boiler. Over here we've got this clearly a commercial building, so we have to use two pressure trolls. One is to operate the boiler on and off, and the other one is to shut off and have an automatic reset should the boiler reach, say, 10 pounds of pressure. Because if the boiler hits 15, it's going to pop that relief valve. And steam boiler relief valves are not like the friendly relief valves we have on hot water boilers that just kind of spit a little. You know, steam relief valve opens with full fury, and it takes that entire load of the boiler and dumps it into the boiler room. This measures 9.9 on the sphincter scale, if you've ever experienced this. Right? So, because what happens too is, you know, I always tell people to work on these things, do not close the boiler room door if you're working on a steam boiler, because if that thing pops while you're working on it, the room is going to instantly fill with like 250-degree steam, displace all the air in the room, and suddenly you're breathing steam and there's no oxygen. So this will kill you in a moment. So you're going to keep the door open so it's got a place to go at least. And then this, you know, we're using more and more probe-type low-water cutoffs, but these old style had to be blown down once a week. That's pretty much why we're using probe types nowadays. Once a week, otherwise they're going to fill up with what we in the industry call schmutz, right? And the schmutz is, once that gets in there, it's going to cause the boiler to fail, because the low-water cutoff can't cut off if you got that stuff inside of it. This was an insurance photograph sent to me by McDonald Miller. The building burned down, and they went in and they found a low-water cutoff, and they said it was never blown down. Boiler dry-fired, turned the pipes cherry red, and burned the building down. So these are boilers that are done really well. These are all pictures of things that guys who are very good at steam put on the wall at heatinghelp.com, which is the bulletin board. And this is called a drop header. And drop headers are used by steam-savvy people because they know the higher you can get with the steam supply and then turn it down, the less water you're going to have pulling out of the boiler. And you will pull a lot of water out of a modern boiler. So that's the way it's supposed to be done. But when you go out in the field, you see stuff like this. Like, you know, where's my 24 inches? And notice how the steam comes out of here pulling the water. The water knows to go right as the steam is going left at 60 miles an hour, because you're going to put arrows on the inside of the pipe to direct the traffic and hope for the best. Well, like this, these people posted this and they said, this Peerless, they don't make good boilers. I said, did you read the instructions? No, you know, because I've been doing this for years. So if you pipe it wrong, or like that, you know, you pipe it wrong and it's going to do bad things. And to demonstrate this, the good folks at Weil McLean for at least 20 years have been dragging this boiler that's piped with Pyrex out to the trade shows. I just saw it 2 weeks ago in Hershey, Pennsylvania. And this is the best display I've ever seen of a perfectly piped, absolutely clean steam boiler. This, what you're about to see, is normal. This is what happens inside your boiler. So it's piped with, you know, not connected to a building, of course, because it's in a tent. But as soon as they fire it up, you can see the water start to percolate out of the boiler and up into those pipes, the risers going up to the header. And then within a moment, it's at that level. And a moment after that, it's at that level. and then it's up there. That's normal. That's why you need at least 2 feet of height from the top of the boiler to where that header is, because this is what's going to happen in a modern steam boiler. And then it cascades over the top. Now, both of those risers are completely filled with water. If your header was lower than 2 feet, you don't have a steam boiler, you have a hot water boiler on a steam system. That's why you can't heat the building. And it tells you all this in the instructions. So that's cascading over into the header, and it's running for a while. And while it's running, what you see here coming out is not steam, that's water vapor. We call that steam, but steam you can't see. That's what steam looks like. That's good dry steam. Dry steam means no more than 2% liquid in it. Dry steam looks like air. When you look in a gauge glass on a boiler, everything above that water line should look like that. It should look like there's air in there. That's dry steam. So this is a boiler producing dry steam, but look at how it's doing it. So this piping that's around the boiler is considered these days to be a part of the boiler. This is the stuff that separates the steam from the water. And you go against those directions at your peril. So my buddy Mike here, he's got about 3 pounds of pressure on the boiler, and he's going to close that valve and show you the effect of quick opening motorized valves that a lot of people like to add to systems to try to zone the system. And when he opens that valve and releases the pressure, it's like shaking up a bottle of Coke and popping a lid. Suddenly, all the water that's in that boiler winds up out in the parking lot. Everybody got their car washed that day. The entire boiler just blew right out of there. And if that was a building, all that stuff would be up in the radiators right now, banging like crazy, having no heat in the building. Right? So, washing down. This guy, see the guy on the phone? He walked right into that. Stop texting, right? So all the while this is going on, when we look at this boiler, if you looked at the gauge glass, it's barely moving. It's moving maybe 1/4 of an inch up and down. But when you look inside the boiler, it looks like a washing machine in there. It's going crazy. So what's going on in your gauge glass is not what's going on inside the boiler. And you got to make sure you get both of these things straight. So it's all about the, many people have said, like, what boiler should I buy? Who makes the best boiler? I said, don't buy the boiler, buy the contractor. And then let him pick the boiler. Because the contractor is going to make or break that job. If this guy doesn't know what he's doing, he's going to put in the boiler using the old piping that was there from the old boiler. And the old piping was meant for a boiler that didn't do this. This is the nature of modern boilers that by federal law have to meet a certain standard in efficiency. Steam boilers used to be 60% efficient. Everybody thought that was great. But now if you got to be up in the 80s, the only way to do that is to reduce the metal. So you're firing the same amount of flame into something that's way smaller, and that's what causes that violence. So you got to follow the instructions. That's my advice to you. And even on the smallest boiler, at another trade show, they had this one. This is what you'd find at somebody's house. It's the same thing going on. So that is normal. And when we get frustrated, we crank up the steam pressure because we can. Because we have screwdrivers that turn only clockwise. To turn a pressure troll. Pressure troll is there to control the pressure. That's what it means, pressure troll. When I was running around doing consulting, I had a counterclockwise screwdriver. I was the only guy in New York that had one. I was. And I'd go in there and crank the pressure troll down. Because when I was younger, learning about this stuff, I'd go up and I'd ask, at the local trade shows, I'd go to the boiler guy and say, how do you set the pressure troll? The guy says, well, you do whatever it takes. I said, well, can you be a little bit more specific? I mean, it's got a cut-in setting on the outside, and then when you open it up, you'll see a wheel on the inside that says differential. So cut-in plus differential gives cut-out, and that creates this sine wave. So cut-in, cut-out, cut-in, cut-out. It's going to make the boiler run like that. I said, why does it do that? Why can't it just come on and run? He says, well, that's because that's the way it does. So finally, the guy gets frustrated. He goes, talk to the Honeywell guy. He makes the damn control. Don't ask me. So I go to the Honeywell guy, and I said, how do you set the pressure troll? He says, I'm going to send you the directions. So this was before internet, right? So I went back home, and I waited for the directions, and they arrived, and I opened them up, and I read, and it said, these are the actual words, set the cut-in scale to the desired pressure. Up to me. So I open it up, and inside there's this little white wheel that's the differential wheel. So cut in plus differential gives you cut out. And Honeywell tells us to set the differential wheel to the number of pounds that the pressure should rise above the cut in scale. So cut in is whatever I desire, and cut out is whatever it should be. Isn't that wonderful? So it took me a long time to figure all this out, and the only way I found it was by reading, and I learned that there was a group called the Carbon Club that was formed basically from the American Radiator Company, whose building is now the Bryant Park Hotel over there on 40th Street, right by Bryant Park. And by the way, that building is built of black stone to look like coal, and the top is castellated to look like the embers in a coal fire. Just so you know, a little New York trivia for you. But in the basement of that, which is now a bar, it used to be a showroom for boilers and radiators, because people came from all over the world to marvel at this thing that would make 72 degrees happen indoors in the winter. That was so unheard of. And they would come like people would go to look at Teslas, or Rolls Royces, to look at boilers and radiators. There was a time when they did that. And at the same time, there were a lot of boiler explosions, because we had very rudimentary relief valves, and we had no rules kind of about pressure. So the Carbon Club forms in the late 1890s, and their purpose, it's all the boiler manufacturers get together and they say, let's come up with a way we're all operating on a level playing field, and we're going to kind of standardize on pressures and temperatures and things like that. So they decided at that meeting, which was held at the Murray Hill Hotel on Park Avenue, it's no longer there, on December 18th and 19th in 1899, they had a 2-day meeting, and at that meeting they declared that from this day forward, all hot water heating systems will operate at a temperature of 180 degrees. They also decided that the difference between a size rating of a steam radiator versus a hot water radiator should be a factor of 0.6. That's why a steam radiator puts out 240 BTUs per hour and a hot water radiator puts out 150. And at that same meeting, they said from this day forward, December 19th, 1899, every steam system in America should run on 2 pounds of pressure or less. That's all you need. And they did that by coming up with pipe sizing charts that established the pressure drop of steam at 1 ounce per loss for every 100 foot of travel. So if you started out with 2 pounds of pressure at the boiler, 1,600 feet down the line, or 160 feet up in the air, you're still going to have 1 pound of steam pressure left at the radiator, which is by definition how we describe the term equivalent direct radiation for radiator sizing, EDR. 1 square foot of EDR puts out 240 BTUs when there's 70 degree air on the outside of the radiator and 215 degrees steam on the inside, which is 1 pound. So the 2 PSI standard became standard, and that's because it's not the pressure that's heating it, it's this stuff called latent heat. So if we have a pint of water, which is about a pound of water, and we want to bring it from 32 degrees up to 212 degrees, 1 BTU raises 1 pound of water 1 degree Fahrenheit. So we have to add 180 BTUs to get to 212 degrees. Now that's not steam, that's liquid water at 212 degrees. To get it to change state and become steam, we have to add an astonishing 970 BTUs per pound to get that to happen, more than 5 times what it took to get us from 32 just to get it to change state, and it's still only 212 degrees. That's the stuff that heats the building. And that's there at 0 PSI. The only reason you need pressure is to overcome the pressure drop as the steam travels through the piping, which is based on insulated pipe and not more than 2 PSI, which they decided in 1899 on December 19th would be the standard. It's called the 2 PSI standard. This is why sensible heat and latent heat are 2 different things. This is why it's the latent heat that heats the building, and it's there for you at no pressure. This is how they heat the Empire State Building at 1.5 pounds of pressure. What's in your building? Why are we running 5 pounds of Mrs. McGillicuddy's 3-bedroom house? Because the air's not getting out, because the air vents are bad, or the steam traps are bad, and some knucklehead's got a screwdriver that won't turn counterclockwise. That's why. So none of this is complicated. All of this is pretty easy to understand. And all the books, everything you need to know is in this room. Up there, you got to get out of your seats and wander around here. Go up there and look around. It's all there, right? If you need me, you know my name, Dan Holohan, @Gmail. Now, I can't tell you why your bedroom radiator's not hot. But I'll be happy to listen to your tale of woe, because it may turn out to be a good damn magazine article for me. So, love to hear from you. Okay, so, how'd I do? Thank you. Well, thank you. Thank you, so generous. Thanks.
Ladies and gentlemen, we will be having a question and answer session, so please speak directly into the microphone and wait for the microphone to ask your question.
If you've got the right questions, I've got the right answers. But I can't solve your heating problem from here.
Yes.
Oh, honey.
I wanted to find out, what's the most exotic steam system you've come across?
The most exotic steam system
Yes.
that I've ever seen?
In New York.
This one's right up there,
Is it?
but also the Dakota, which the Dakota was, the Dakota was named that because the architectural critics said no one will ever live there. It might as well have been in Dakota.
Yeah. No,
But that had
my father actually put the boilers, when they moved it from the outside power plant.
Yeah, there was a steam
inside.
engine. They had a steam engine
Right.
in 1884, and the steam engine made electricity, and they used the waste steam to heat the building, and with the same system that's in this building. And also, they sold steam and electricity to people around them as they moved up there, and that was one of the first cogen plants. That was a fascinating building. I also looked at Doris Duke's house in New Jersey, which was on thousands of acres, and probably the most elaborate mansion I've ever seen in my life from that time. And she had that indirect heat where it comes in from outside and wafts over the metal and goes upstairs. And that was interesting because the gardener had put fiberglass over it, plexiglass over the top of the outside air inlets, and then topsoil, and planted pachysandra over that, so there was no air coming in. And the plumber put a fan behind the heater trying to blow the heat upstairs. She had it was like 110 people living there in that estate just to take care of her, and there was like every trade. So I went outside and I found out where the gardener had covered these, and we just moved the dirt, lifted the panel, and the whole house heated. So that was pretty exciting.
Dan, I know a lot of people know about heatinghelp.com, but for those who don't know, could you just explain the wall? Because it is such a wonderful resource.
We started this website in 1997 when the internet was new, and it just grew into this massive collection of information. And there's a bulletin board on there called The Wall that last year there were 2.6 million people on that bulletin board, unique users. And if you have a question, it's a place where there's no fighting or flaming or any of that. We grew past that years and years ago. But if you've got a question, you're going to get an answer in moments. It's not like you got to come back tomorrow. You'll get an answer in a matter of minutes, because there's people that just have no lives like me. We just sit looking at the thing all day long. In fact, if you want to come to something fun in August, we're having an event called Wet Stock in this room, and it's a gathering of people that talk to each other on that site, that are going to come together and meet in person, many of them for the first time. But this is a collection of the brightest people in this industry, all being in the same room. And we've done this in years past in lots of cities across America, and it's always like this incredible dynamic atmosphere. And there's people coming as far away as Alaska to be in this thing, right in this room. So there's no lectures. It's just people sitting at round tables talking about different topics, just moving around, and there will be food and beer and wine. And that inspires people to talk even more. So that's August 24th in here. So if you want to come to that, there's still a few tickets left. So.
Hello, Dan. What are your opinions on TRV, thermostatic radiator valves?
I think they're wonderful.
Yeah, in fact, the ones we used here were from Macon, which is sold by Tunstall up in Chicopee, Massachusetts. And they, in a system that's two-pipe air vent, where you've got steam in both the risers, and that airline that used to pull the air down, like the Dakota did with the steam engine, they used an ejector. We don't have that line in operation anymore, so there are radiator vents on all the radiators, but we put the TRVs in between the radiator vent and the radiator. So rather than control the amount of steam going into the radiator, we control the amount of air coming out of the radiator, because where there is air, steam will not go. So when a room comes up to temperature, the TRV shuts the air vent and keeps some air in the radiator so it can't overheat. And I think we've got happy people, and it's quiet. I mean, when I first came in here, it was banging like crazy. So we cut the fuel bill basically in half. We have balance. We've got comfort everywhere, and quiet. That's the way steam's supposed to work. All right? Yes?
Hi, I just have a question. When you were doing all this reading in the past, did you ever come across any system or component that you thought was just brilliant that was not ever used in reality?
So many, and you know, you examine patents and you see things, you say, man, this is such a great idea, but it just never came to be. And a lot of that has to do with sociology, because the big steam era lasted from like 1905 to about 1930. So what we call the vapor era, there were dozens of manufacturers making specialized equipment to operate systems at extremely low pressure. And that only lasted 25 years. And then we went into depression, so there was very little being done then. And then we went into World War II, and they were actually pulling radiators and pipes out of buildings to use as scrap. You know, there was these big scrap collections. And then after World War II, we had the development of the suburbs, and that all went with furnaces, for the most part, you know, except for areas like Long Island, New York, and you know, most of the rest of the country runs on furnaces. So prior to World War II, 50% of the buildings in America were heated with steam or hot water. After World War II, it dropped down to about 11%, where it has remained since after World War II. I mean, I got involved in the heating industry in 1970, and our percentage, the hydronic percentage, was 11%. That's what it is today. So it's what I lovingly refer to as a profitable non-growth business. You know? So that's what's going on. Yes?
Many New Yorkers are worried about the new Green Deal, and I'm wondering whether steam buildings can meet the guidelines of a new Green Deal. It seems you were able to do it, right? Reducing usage by 40%.
Yeah, and I had some of the city people contact me because I'm known for this, and I said to them, I know you want everything to go P-tax like you have in motel rooms, you know, that type of heater. That's what they want to put in city housing and everywhere, and everything should be electric. That's the movement. Everything should be electric. I don't know how you do that without rewiring the whole city. Also, I said, in the interim, you know, as you're moving in that direction, how about you come here and I'll show you this. I'll walk you around and I'll show you this, what we did. And we did all of that work with no cost to the society. Everything was, I mean, we needed a couple of heat exchangers to take the heat out of the domestic water and to take the heat out of the condensate to heat all the domestic water we need before dumping it into the condensate down the sewer. We reclaimed that. We changed some piping in the basement to put it back to 1890, and we put the thermostatic radiator valves on. But with very little expense, we cut the fuel bill basically in half, and they were not interested. They said, we've made up our mind, we're not interested. They didn't want to know. They didn't want to talk about it, they didn't want to see it, they had made up their mind. And when they were first talking to me about the steam, I realized they didn't even know what they're talking about. You know, they don't understand. I said, there's things you could do to tweak these systems to get remarkable difference. Sometimes you fix one air vent or one bad steam trap and everything starts to work. But you got to look at it as a system. But there was no interest whatsoever in that.
Oh my goodness.
So, you know, I'm an old retired guy. I just shrugged and said, well, there you go.
Yeah. I do read in this little handout that this building is no longer running those boilers, that you're buying steam from Con Edison.
Yeah, that was done in the 80s.
when the boilers, it was before our time, but the boilers are still down there because those boilers were put in when the building was built. So those boilers are 20 feet long, 10 feet high, and 10 feet wide. There's no way to get them out short of, breaking them up.
Okay, so the energy savings is the adjustments you made, they reduce the cost of paying Con Edison for the steam.
Measures the steam with a meter as it comes into the
okay,
building.
yeah.
And as soon as we made these changes, they sent somebody around right away to change the meter, which delighted me. Anybody can do that. Yes?
This may be not an easy question to answer, but I live in a 1954 era building, steam heat, and the convectors now are starting to fail. So we're looking at replacing probably most of them. What do you recommend as far as temperature regulation? That's something easy for the resident to adjust because they're covered. They're covered convectors.
Yeah, is it one pipe steam?
One pipe steam.
Yeah, so you get the thermostatic radiator valves that go between the radiator and the air vent, like we use here in this building. And they come with remote sensors, so you can have that on the outside. Just mounts to the wall.
Gotcha.
Don't put the remote sensor on the radiator. I've got photographs of that. It's just.
Any brand you recommend for that?
We had really good luck with Macon.
Macon.
M-A-C-O-N.
Okay.
Through Tunstall and Chicopee. They're like the national distributor for Tunstall, like the singer. Chicopee, Massachusetts. They're good people.
Macon.
Thank
you.
You're welcome.
I got a question. Have you had a situation where basically somebody took the steam boiler out and replaced it with the hot water and used that while the rest of the system was designed for the steam?
Did they do anything upstairs, or they just changed the boiler?
They just changed the boiler and they're pumping hot water into the system.
That's right up there with who gets to work in America.
Last question.
Oh, she's going that way. I'll be here.
I was actually going to follow up about that topic. I wanted to get your opinion on steam to hot water conversions as a method for energy efficiency, even for things such as the Green New Deal. And then I was kind of curious, maybe what's the largest steam to hot water conversion you've seen work successfully?
Okay, so preface it by saying that what we did here in this building, which is pretty darn green, right? And again, we didn't have to rip the place up. So we got to keep the beautiful old radiators and still save that much money. So that's great. Now, if we were to convert this to hot water, it's a 7-story building, so we would be putting much of it under the static pressure of the water, which will find every leak that you don't see if you're operating very, very low pressure steam. So leaks come out. We would have to also deal with balance. So we would have to have balancing valves. And also, the boilers that we would probably put in would be what are called modulating condensing boilers, which is, that's the green standard these days that operate in the high 90%. But they're also expected to live maybe 10 years. I mean, that was, I traveled a lot in Europe looking at heating, and 20 years ago when these things first came out, I asked the big manufacturers, how long will these things last? And they said, 10 years tops. I said, well, in America, we've got boilers that have been in for like 80 years. And he says, yeah, but that's old, 10 years. I said, but how do the people feel about that when they got to rebuy the thing every 10 years? He says, well, there are laws here that say they have to. So, and we're getting to that point. We're getting to the point where we're putting A, B, C grades on buildings like they've had in Europe for 20 years. In Europe, if you live in a home, you're visited every 6 months by the chimney sweep, who comes to your house and he does an analysis. He's a private contractor that's licensed by the government. You have to let him in. He has the power of the police. And he does an efficiency test on your boiler. And if you don't pass that test, he red tags the boiler, and you now have 2 weeks to have the boiler replaced. And if you don't have the boiler replaced, the guy comes back in 2 weeks and takes the boiler out of your house. Are we going in that direction? It's interesting. But where is really the green savings if we're replacing this thing every 10 years? And what are we doing with the old one? Putting it in a landfill? Because they're not recycling them. And the service required on those mod-cons, modulating condensing boilers, is far more than we need on the stuff that we've been using. So that means there's more trucks driving to places to service, which means there's more gas being burned, more traffic in the city. All these, big picture stuff. This is like, look at the whole system, not just one part. So if you're looking at only the boiler and you say, I can get something at 95% when the steam boiler's at 85%, that's the way to go. Well, maybe not if you got to replace the thing over and over and over again, and maybe not if you got to rebuild the whole building in terms of piping and radiation. That's just my old man opinion. Great question.
It's interesting, even when you were saying HVAC is not regulated in terms of the contract.
Yeah, Victoria's saying it's interesting because HVAC is, certainly heating. It's not. There's no heating policeman here. There's a plumbing inspector. There's an electrical inspector, but nobody comes to look at the heating. They look at the gas. If you're burning gas, the guy's going to look at the gas, but only at the gas. He's not looking at the building. So if you just did a little bit of studying or just went on heatinghelp.com and hung out on the wall for a while and just listened to these brainy people talking about everything they're doing and showing photographs of what they're doing, you'll just absorb it and you'll be able to do what other people say can't be done, because that's what we did here. And this is such a typical building in New York. You don't have to be genius, you just have to read. Stop texting. Thank you. All right, we're done.
We are so grateful for you being here this evening and sharing your expertise and experience with us, the audience. Thank you so much. And just before you part, we'd just like to make a short presentation, if I could just have your attention for a minute. And to do so is Victoria Dengel, our Executive Director.
Dan, we've kind of run out of ways to thank Dan, and let's just first say that 4 years ago, boy, was that a fortuitous situation when Joe Marciano was here tonight, suggested you need to meet Dan Holohan. And really, Dan, you know how we feel about you. You're heaven sent. You're brilliant. So Dan didn't want any certificates, no lifetime library memberships. But I was raised in an Italian household, and you never go to something empty-handed. So we came up with something. There's a book that we have that talks about our lock collection, written by one of our members, called American Genius. So I think that's a good name for you, or we did. So we say, Dear Dan, with every best wish to our American genius. So thank you. Thank you, Dan. And so thank you, Dan. And I just want to say something to all of our guests tonight, especially those who are visiting here from the plumbing and the heating industry. It's really, one of my roles here is the director of Mechanics Institute. And it's so exciting to hear this in terms of information, to have a mind like Dan's, to hear the exchange of our students here in the Mechanics Institute. It's a brilliant industry. It really is. When you learn it inside out, it's academic. I'll never forget one time somebody said to me, this was someone who came to one of our events, there's a plumbing theory course, and I was like, yeah, how do you think the water gets to your sink, and much more. So, wow. So to all our people in the trades here tonight, a very special welcome to you. As I always say, nothing would happen without labor in this city, and I grew up as the daughter of an operating engineer, so proud to be a part of the building trades. Dan, so blessed to have you really as a gift to the industry. So thank you, thank you, thank you.
Thanks, everybody.